Hello, vintage computer friends, and thanks for tuning in again into my YouTube channel where we experience and explore the early 1980s educational computer systems of West Germany. And today again we have the 4-bit Busch Microtronic computer system on the bench. We had a number of videos already on my channel where I introduced you to Busch Microtronic machine language programming, and the pinnacle of this hands-on programming experience was the implementation of the recursive version of Towers of Hanoi. And we already got the impression that this machine is not the fastest, right? But how can we actually quantify this impression? I mean, a common measure for CPU or computer performance is, of course, MIPS, million instructions per second. So what do you think, how many MIPS will we be getting out of the Microtronic? And how do we actually measure MIPS? So the machine is not the fastest, and this is because, I mean, it is not executing native TMS 1600 machine language, but it's a masked programmed ROM which contains the monitor program and a virtual emulated educational machine language. So all of this is not native machine language, but a virtual machine language for an emulator that is running on this TMS 1600 microcontroller that's clocked at half a megahertz, so 500 kilohertz, yes, very slow. So let's see how we can measure this, and I already have my oscilloscope set up, right? And the oscilloscope is going to help us with, quantifying the number of instructions that this machine can execute per second. And one way of doing this is to utilize the digital output ports. See, the machine has a 4-bit digital output port here, right? Also with 4 LEDs, and I have connected the oscilloscope to bit 1, the first bit of this 4-bit output port. And ground is also connected, that is a black wire. And now all we got to do is write a program basically that outputs a square wave on the digital output port, and the oscilloscope is able to tell us then the frequency, and from there we can deduce basically, so the frequency of course is measured in hertz, and from there we can then deduce the number of instructions per second, right? So what we are going to see is the time, or the hertz number, determined from same state to same state, right? From 1 to 1. But in between something happens, right? I mean, a number of instructions need to be executed. First we need to set the output bit to 1, and then we need to set it to 0, and then we also need to execute a jump basically. So we need to multiply the hertz number then with the number of instructions that it takes to recreate the same one state at the output. And let's start entering this program. So I zoom in a little bit here, you can see the display better. And so the first thing we are going to do is, with FO2, we turn off the display, because multiplexing the display at runtime takes time and it slows down the machine. So let's start by having the display off at runtime. And now the fastest or simplest way to produce that square wave is to preload the registers with 0 and 1. So we are loading 0 into register 0, and we are loading 1 into register 1. And now FE is the dot opcode or instruction data output, and at outputs the value that's stored in the specified argument register, in this case 0, right? Since 0 contains 0, we will then have 0 at the digital output port, meaning that also our first bit here will be off or in low state. And then we are using FE1 to output the value that's stored in register 1, which is 1, and causing the bit 1 then to go into high state, and the oscilloscope will be observing that. And now we just execute a loop, go to 0,3, so we just keep iterating this in a loop so that we produce a square wave. Okay, let's actually start and run this program and see what the oscilloscope is telling us, what kind of frequency we get from this program. And there we have a very nice square wave now on the display, and the oscilloscope can also tell us the frequency. It's already displayed here. Let me zoom in a bit. So it tells us 38 Hertz. So, and 38 Hertz, right? This is for 3 instructions now. Output register 0, output register 1, and jump back. So we gotta multiply 38 by 3. And what do we get? 38 times 3 is like, yeah, 114 instructions per second. And this is as tight and fast as you can toggle the digital output ports with a Microtronic. It's not possible to go faster than that, right? And not all the instructions takes the same time, but at least that gives us now our first number. So 114 instructions per second. Let's just write that down. Let's also see what happens if we turn on the display at runtime. So if we only display a single digit on the 7 segment display, then you see that the frequency is now already reduced to 27 Hertz, right? And 27 times 3 is 81. So we already lost quite a bit of performance, and it even gets worse if we turn on all 6 digits on the display. Now the Hertz number is down to 13.9, say 14 Hertz. So yeah, that's quite bad. So with all digits turned on, the machine actually performs at 42 instructions per second. As you can tell, we are far away from achieving MIPS. We are actually more in the, let's say, HIPS, hundreds of instructions per second realm. So about 0.4 HIPS if the display is fully enabled with all 6 digits shown at runtime, and up to 1.2 HIPS if the display is turned off, but we can't go faster than that with a Microtronic. And that also depends on the instruction that's being executed. Not all instructions take the same amount of time. For example, the machine has multiplication and division, and if you divide 9,999 by 1, the machine actually takes 40 seconds, right? So that's of course incredibly slow. This is just a simple implementation that subtracts 1 in a loop 9,999 times. Obviously not the best implementation, but well, it has a useful division opcode, and speed is not everything. The machine is still highly interesting and useful for educational purposes, as well as for performing basic physical computing things, right? Okay. There's another way, of course. We could write another program to get that number. So let's try another way. How about we implement a counter? Again, we turn off the display first. And well, if you have a 4-bit counter here now, sorry, the keypad is a little bit bouncing. So we add 1 to register 0, and then we output register 0 to the digital output ports, and then we jump. So it's just a tight loop again of 3 instructions. Add 1 to register 0, output register 0, and jump back, right? So 3 instructions. But if you look at the bit patterns for counting, you will of course know that the bit now toggles and goes from 1 to 0. So it's 1 for odd numbers, 0 for even numbers. So you gotta multiply this by 2 now, because you now need not 3 but 6 instructions in order to reproduce the same 1 state on the oscilloscope, right? And this is what it measures. So let's run this, and we can nicely see binary counting going on here with the output ports. And what we see is 19 Hertz. And if we multiply this now by 6, then we are again like in the similar region as we were before. Yeah, exactly 114 instructions per second. So even the addition of a constant to a register takes about the same amount of time as the other instructions that we used. Go to as well as output register to digital output ports. Another interesting number that we can maybe compute is say the emulation overhead, if I may call it that way. See, the DMS 1600 CPU is clocked at 500 kilohertz, so ideally that means it could maybe execute 500,000 instructions per second. Of course, this is a very coarse upper bound, right? And it's not going to do this because usually to execute a native machine opcode takes a couple of cycles, something like fetch, decode, execute, store back, deal with the memory, all these kinds of things. But it's interesting to kind of nevertheless compute this factor. So if we divide 500,000 by 114 or 1.1 hips, then we are getting a factor of 4,385, which we might call the emulation overhead. Okay, so that's it for today, folks, and I'm going to repeat the same experiment with the Cosmos CP1. Let's just keep in mind the upper bound for the speed that we determined, 114, and the emulation overhead was in the realm of 4,000 to 5,000. Alright guys, until next time, thanks for watching, bye.